Hey guys, and welcome to a new series today where we're going to take a look at the June 2019 Further Maths Core Pure 2 paper. So this is the A-level exam, not the AS. So if you've only studied the AS, this might be a bit past the scope of what you've learned just yet. But be sure to subscribe. We're going to be going through the AS and the A-level papers in full. So check them out when they're up. So anyway, let's jump into question one. So we have a question here on hyperbolic functions and specifically hyperbolic tan. So part A for question one just asks us to prove that the inverse of hyperbolic tan is equal to a half ln 1 plus x over 1 minus x. And we have the stated value of the constant k here. But we'll do that at the very end once we've shown this is true. So 5 marks. So let's jump right into this. So we've got to prove that the inverse of hyperbolic tan is equal to this. So what I'm going to do first is I'm going to let y equal this expression here, this hyperbolic tan inverse. So hyperbolic tan inverse of x. Okay, so if I times both sides now by hyperbolic tan, what I'm going to get is hyperbolic tan of y. So this would be hyperbolic tan of y, and that will just be equal to x now. Okay, because if you times this side by hyperbolic tan, they'll just cancel. You just get left with x. Now we've got hyperbolic tan of y. So now we can use the trig identities that we know for hyperbolic functions. So this would be the same as hyperbolic sine over hyperbolic cos. So plugging in those exponential definitions now, what I know is that x is going to be equal. So I'm writing this in terms of exponential now, the exponential definitions. This will be e to the y, because it's in terms of y. So e to the y minus e to the minus y, divided by e to the y plus e to the minus y. Okay, so just be careful you get them the right way around. E to the minus y. So we've got our exponential definition now. Now all we need to do is start manipulating this. And it's good that we've got this in terms of the exponential now, because we're going to have to do antilog at some point to get the ln, right? So we know we're on the right path with this. So now I can times through both sides by, well, think about this as being 1 over e to the y. So I'm going to times through now by e to the y on this side here, just to get rid of the minus y here. So what that would give would be e to the 2y minus 1, because this is minus. So that gives me minus 1. And this will be e to the 2y plus 1. So hopefully this is all still pretty straightforward. Just for now, I'm just timing through by e to the y. So therefore, I'm going to times now both sides by e to the 2y plus 1 to get rid of this denominator. So I'm going to have x lots of e to the 2y plus 1. And it's going to be equal to e to the 2y minus 1. Like so. Now I'm going to times through here on this left hand side to get this in terms of x. So that'll be x e to the 2y plus x, and it's going to be equal to just e to 2y plus minus 1, sorry. Now here, I want to get this in terms of e to 2y just on its own on one side, so then I can antilog. So to do that, I'm going to take this e to 2y across here. So if we do that, in fact, what I'll actually do is I'll take this x e to 2y across onto this side, and then I'll keep this as positive, so it'll be x plus 1 on this side. So if I do that, that's going to be e to 2y minus x e to 2y. So I'm just going to get this all in terms of e to 2y now. This will be equal to x plus 1. So x plus 1. Now I can factor out the e to the 2y. So e to 2y. That's going to be 1 minus x. So 1 minus x. This is still equal to x plus 1. X plus 1. And now I can divide through by 1 minus x. So I'll do it over here just so we've got a bit more room. So e to 2y. That's going to be equal to, I'll put it all in, all over the same one. So it's going to be 1 plus x all over 1 minus x. Like so. Now I'm going to anti-log, and this is looking pretty good, right? We've got 1 plus x over 1 minus x, so we're nearly here now in this form. So if I anti-log this now, what I'm going to get is I'm going to get 2y is equal to ln of 1 plus x over 1 minus x. And then finally, just divide through by 2. So therefore, y is equal to ln, half ln, got my half ln of 1 plus x over 1 minus x. And there we have it, because we said at the beginning y is equal to the inverse of hyperbolic tan. And for part B here, well, before I start part B, for the value of the constant k here, for this limitation, think about what's going to happen here. So this is logarithms, right? So if you think about the rules of logarithms, this would be two separate ones. There's going to be ln of 1 plus x minus ln of 1 minus x. So we've got to think about what values can go in here. Well, I can't have these values, this ln here, be 0, ln of 0, right? Because that would be an error. So, for example, this top one here, 1 plus x, my x can't be 1, right? But it could just be underneath 1, because these, you know, we're not including the k as well. So, for example, if k is 1, then it'd be fine here, because it'd be just less than 1. So 1 minus, say, 0.99999, that won't give us an error. But if it was 1, for example, so 1 minus 1, so we'd have ln of 0, we'd get an error. So for your k value, it's just going to be 1. So it's between minus 1 to 1. So jumping into part B now, we're going to use our answer to part A to solve this equation here. So for another 5 marks for this. So quite a nice introduction to the paper, I'd say. So let's jump straight into this. So we know that 2x equal to hyperbolic tan of ln square root 2 minus 3x. So I can now use our answer for here. But in terms of it being, how it's in terms of x here, we just need to put it in terms of 2x. So times in both sides by hyperbolic inverse of tan. So that'll be tan hyperbolic tan inverse of 2x. So be careful here, 2x this time. And then this will just give us ln here, because you've got hyperbolic tan times by the inverse. You're just going to get left with what's in the bracket here. So it's going to be equal to ln of square root 2 minus 3x. Ln 2 minus 3x. Perfect. So now we can start going with this. But when I've got this hyperbolic tan inverse, I need to substitute mine in. But instead of it being 1 plus x, for example, whereas an x, it'll be 2x in our case. So if I write this down now, this will be a half ln. So it's going to be 1 plus 2x, 1 plus 2x, all over 1 minus 2x, like so. Okay. And then this side will just be this still. This will be ln square root 2 minus 3x. 2 minus 3x. Now I can use the power rule for logarithms. So this half here can come up to the top of the logarithm. So that's going to be ln 1 plus 2x all over 1 minus 2x all to the power of a half. All to the power of a half. And this is going to be equal still to this. So ln 2 minus 3x. So now we need to start solving this equation. So we've got logs on both sides. We can anti-log this now, and then we'll get it just in terms of in terms of our x here. So anti-logging this, we're just going to get left with the expression. So I'm going to get 1 plus 2x, so do it over here, 1 plus 2x, all over 1 minus 2x, and I'll put this in brackets, because this is still to the power of a half. That's going to be equal to 2 minus 3x. So now, because this is a power of a half, I can square both sides here. Oops, I forgot my square root. Square root there, so don't forget your square root. So now I can square both sides here. So I'm going to get 1 plus 2x over 1 minus 2x. And this is going to be equal to 2 minus 3x. Now, times in both sides by 1 minus 2x, we can eliminate this denominator here, and then just solve for x, and we've got it there. So, it's going to be 1 plus 2x is going to be equal to 1 minus 2x times 2 minus 3x. Like so. And now we've just got to solve this. So if I expand all this and then simplify it, what you'll get is 6x squared plus, minus 9x plus 1. And this is equal to 0 if we're solving it. So you'll need quadratic formula for this. This won't factorise nicely. But if you use your quadratic formula, so we'd say therefore x is equal to, now you normally say plus or minus, right? We normally use plus or minus for the start of the equation. But when you're plugging in your values here for your quadratic formula, make sure you test it, because remember, x has to be between minus 1 and 1. If you get a value bigger than, say, 1 or smaller than minus 1, then something's gone wrong. So what that actually does is it eliminates the positive solution here. So what we get is 9 minus root 57 all over 12. So you've got to test this on your calculator. So make sure you do 9 plus root 57 over 12, 9 minus root 57 over 12, and you'll see the difference. The 9 plus root 57 over 12 is out of the range here for x. And there we have it. That's question 1 fully complete. On to question 2 now. We have a question here dealing with the roots of a polynomial. And in this case, we have a cubic polynomial here. So we're told the roots are p, q, and r, and we're asked to find the values of 3 separate expressions here. And it's 8 marks in total, and we're told not to solve the equation. So we've got to know the rules for the roots of the equation, okay? So if we write these down first, I'll write them up here. So if we do them up here, so remember, for a cubic now, and we've got 3 roots, we've got p, q, r, so that's going to be equal to minus d over a, so minus d over a. We're also going to have pq plus qr plus rp, and that will be equal to c over a. And then finally we're also going to have p plus q plus r, p plus q plus r, and that's going to be minus b over a. Okay, so these are the 3 expressions that we're going to need to find the value of these 3 expressions. But let's actually work them out now, because we know it's minus d over a. Well, it's ax cubed minus bx squared in this case, plus cx minus d. So minus d over a, so if my d here is this minus 5, this is going to be minus, so it's going to be minus 5 over 1, so that's going to be 5. Okay, so that's just equal to 5. This one, I'll just do it over here. So c over a, so 4 over 1, so that'll just give us 4, nice and easy. And then finally, I've got my p plus q plus r, so that's going to be minus b over a, so it's going to be minus 2 over 1, so that's going to give me positive 2. That's positive 2. Okay, so we've got our 3 values. Now we need to find the value of these 3 expressions here. So 2 over p plus 2 over q plus 2 over r. So this one is pretty straightforward compared to the last one especially. For this one here, this is very common for the cubic one. So if you've gone through the Corpio 1 and 2 textbooks, you'll have come across this form before. Okay, so this is very common. The way to find the value for this one, well, straight away in the numerator we've got a 2. Now we're always going to use these expressions that we've worked out here: pqr, pq plus qr plus rp, and p plus q plus r. So straight away the big obvious one for me is that we're going to need 2 lots of whatever it is in the numerator. Okay, so it's going to be 2 times something. Here now, I've got a choice of these 3, okay, and we're going to have to get something to cancel, because we've got no letters in the numerator, okay, so they've clearly cancelled at some point. So, in my numerator, if you think about it, I'm going to need this expression here, pq plus qr plus rp, because what I'm going to do is I'm going to put underneath in the denominator a term so that I can cancel 1 from each. So what this will look like, if we write this down, it'd be pq plus qr plus rp, okay, and then this will be divided by another expression. Now this expression, it's got to be one of these 3, and clearly it won't be this same one again, so it's a 50-50 now between these 2. Well, if we start up here, if I put pqr, I can then split this up into 2 separate fractions, right, because it'd be 2 lots of pq. Okay, if I write this down, pqr, well, if I've got 2 pq and I divide it by PQR, I'm just going to get left with 2 over R, for example. The PQs will cancel, so I get 2 over R. Same again as you go across. So this is going to be equal to 2 lots of this, so that's 2 lots of 4. So 2 times 4 all over PQR, so that's 5. So I'm going to get 8 over 5. And there we have it, that's part A done. So let's have a look at part 2 now. So part 2, we've got these three brackets here, sorry. Now, if you ever get brackets, straight away think about expanding them, okay? This is the best way to go with the brackets. So if I expand this, I'm going to get PQR. Now, don't forget this. What I'd do first is I expand the first 2 brackets, then expand it with the last one. So I'll do that over here. What that'll give me PQ minus 4P minus 4Q plus 16. And then I times that by R minus 4, so R minus 4. Okay, and then as I expand each term, so I'd get PQR, and so on and so on. So I'm going to get so I write them all down over here. So I'm going to get minus 4PQ, minus 4PQ, minus 4PR, minus 4PR, plus 16P, so plus 16P, minus 4QR, minus 4QR, plus 16Q. So again, I'm just slowly expanding everything across here. Plus 16Q, plus 16R. I've just finally run out of room for the last term, and I've got a minus 64 there, okay? So minus 64 at the end here. Here now, I need to try and get these into terms that I can work with. Notice I've got my PQR here at the beginning. So this is already in a form that we can work with, so that's good. The rest of it, though, needs sorting out. We can't work with this just yet. So if I write this down, we've got PQR. That's fine. Notice how I've got a lot of multiples of 4 here, and I've got a couple of 16s. So what I'm going to do is I'm going to break these up into 2 separate terms, right? I'm going to have my 4, I'm going to factorise that out. I'm going to factorise the 16 out as well. So if we do that here now, it's going to be minus 4 lots, because it's minus 4 for each of them. So minus 4 lots of PQ plus PR, well, yeah, plus PR in the bracket, and then QR as well. So if we write that down, PQ plus PR and plus QR. So that looks good. We've also got the plus 16P and the plus 16Q and the plus 16R. So if we write them down as well, plus 16 lots of P plus Q plus R. And then finally, we've just got this minus 64 on the end here now. And this is looking much better. We can now work with this. Because this PQ plus PR plus QR, we've got that here, that's 4. So what I've got now is PQR, which is 5. 5 minus 4 lots of 4, because that's 4. So that's minus 4 lots of 4. And I've got 16 lots here, so plus 16 lots of 2, because P plus Q plus R is 2. That's 16 lots of 2. And then finally we've got a minus 64 at the end. And if you evaluate all of that, you're just going to get minus 43. And there we have it. That's the second part done. And now finally, we get to the very last part of this question here. P cubed plus Q cubed plus R cubed. So this is definitely the trickiest of the 3. But again, just like the other 2, you have to use the previous expressions that we've got up here. It's always the same method. You need these to figure it out. So, working this out now. Well, I can change this now. It's P cubed plus Q cubed plus R cubed. That would be the same as P plus Q plus R all cubed, right? So P plus Q plus R all cubed. At some point in that expression there, I will get P cubed plus Q cubed plus R cubed. But obviously with this expression, I'm going to get a lot of other terms that we don't want in the expression, okay? So what I'm going to have to do here is write everything out and then just try and factorise. So it's definitely the trickiest of the 3. Now this, with practice, you'll kind of just get a hang of how this will actually factorise with enough go at these questions. But again, if you're completely uninitiated with these questions, this would be the best way to do it, okay? So if we do this now, and I'm going to expand each term here. So I'm going to get a P cubed plus Q cubed plus R cubed. Okay, so I've got P cubed plus Q cubed plus R cubed. And again, I'm just going to expand on this. I've already done this on paper, but this is what you'll get for each term. So you'll get plus 3 lots, my writing's going a bit funny here, plus 3 lots of p squared r, plus 3 lots of pq squared, plus 3 lots of PR squared. Okay, so that's looking pretty good so far. What we should hope for, again, is something similar to this part B here, where we get a lot of 3s, or a multiple, for example, which we can then factorise out. I'm going to also get plus 6 PQR. So hopefully you can see on this graph, so that's plus 6 PQR here. I'm also going to get plus 3 QR squared. And then I'm going to finally get plus 3 Q squared R. 3Q squared R. Okay. So now we need to have a go at tackling this factorisation. Okay, so we still want the P cubed plus Q cubed plus R cubed. So we keep that at the beginning. So that's what we need at the end. I'm also going to get, now notice here, we've got all these 3's, right? And we need to get rid of them. So we're going to have to subtract them off, right? So what I'm going to do is I'm going to do minus 3 lots of them. Minus 3 lots. Okay. And now for each one of these, there's going to be obviously a second bracket as well, because we've got P squareds, we've got Q squareds, and we've got R squared. So I'm not going to be able to factorise it all as one. So what this will be is it'll be a product. And in the first bracket, I'm going to write it as P plus Q plus R. Because again, remember, we have to use these expressions here. P plus Q plus R, and PQR and PQ plus QR plus RP. We're going to have to use them at some point. So if I do this now, there's going to be 3 lots of P plus Q plus R. Now the good thing about this is, when I expand this with my next bracket, we're going to get the squareds in here. So this is the good thing, okay? And then in my next bracket, again, we're going to have to use one of these expressions. But the obvious one would be my PQ plus QR plus RP. And the reason for that is because when I times it through by this bracket now, I want them to give me the squared terms, okay? Whereas when I times it, if it was PQR, for example, it wouldn't be particularly pleasant, okay? I'd get some, I'm going to get every term in each multiplication, so that's not what I want. So it's going to be PQ plus QR plus RP. And at the very end, so think about expanding this out, right? You get minus 3 lots of P squared Q, for example, here, because you get minus 3 times P times by PQ. Now at each point, I'm going to get a P times an RP. So I've got P times QR, so I've got PQR. I've got a Q times RP, so I've got QRP. And now at each point, this is times by 3. So I've got 3 lots here times by 3. So I'm going to have 9 lots in total. Now we add 6 lots on, so I've got minus 9 lots. I add 6, so I'm at minus 3, so I'm going to have to add another 3 lots on, just at the very end here, just to get rid of it in total. So that's 3 PQR. Okay, so we're nearly done with this question. It's quite long, and my cat's meowing, so I'm going to have to try and get it done now. So we've got all the values that we need. All we've got to do now is just substitute the values in up here. So this here, again, it's like we said, this is P plus Q plus R, all cubed. So P plus Q plus R, all cubed, minus 3 lots of P plus Q plus R, which is 2, so minus 3 times 2, times it by PQ plus QR plus RP, which is 4. And then we're going to plus this with 3 lots of PQR, which is 5, so 3 lots of 5. So P plus Q plus R, that's 2, so this is 2 cubed minus 3 times 2, which is 6 times by 4, minus 24, plus the 15 here. Evaluating all this, you're just going to get minus 1. And there we have it, that's question 2, fully complete. Moving on to question 3 now, we have a question here to do with integration, and it's related to the hyperbolic trig functions, and it's using substitution. And we're asked to state clearly what that substitution is. And then part B is just a dead brief one on the mean value theorem. Okay, so just 2 marks for that. So let's jump into question 3A. Let's have a go at tackling it. So we've got f of x is 1 over the square root of 4x squared plus 9. And we have to use this a substitution here, that should be stated clearly, to give the integral of f of x dx being equal to a hyperbolic sine inverse bx plus c. So, to get my substitution, if I do it over here, I'm going to use a right angle triangle. If that's my right angle there, and my largest length here, that's going to be 4x squared plus 9. Okay, well what that must mean is that one of the sides must have been the square root of 4x squared, so 2x, and one of them must have been the square root of 9, so 3. Okay, now I can get this in terms of tan theta, so tan theta, well, what will tan theta be? Well, that'll just be opposite over adjacent, so 2x over 3. Okay, and then we can now put this in terms of x for my substitution back into f of x. So x is going to be equal to 3 tan theta over 2. And next step, because we're using substitution, let's work out dx as well. So dx, what will dx be? Well, that would just be 3 over 2 sec squared theta d theta. Okay, so we've got all the preliminary kind of like information we need for this question. Let's jump into actually substituting this now. So, going over here, I'm integrating f of x with respect to x, so it'd be the integral now of this dx. Okay, so integrating this now, all I'm going to do is substitute my x equals into here, and I'm going to put dx on the numerator. So, what I've got now is dx over the square root of 4 lots, squaring x now, so that's going to be 9 over 4, tan squared theta plus, I've got the 9 as well, plus 9. Okay, so I kind of underestimated just what I needed there for that, so there we go. And don't forget, this is going to be with respect to theta once I put my dx in, okay? So if we do that now, this is going to be the integral of 3 over 2 sec theta, sec squared theta, sorry, d theta. And this is going to be over this now, but I can simplify here. If you've got 4 lots of 9 over 4, that'll just cancel to give you 9, and I've got 9 tan squared theta plus 9, okay? So I can actually factorise in the denominator. So this will give me 9 tan squared theta plus 9. Factorising that now though, that's actually going to give me, so keep the numerator the same, 3 over 2 sec squared theta. My denominator now, well that's going to be the square root of 9 lots of what tan squared theta plus 1. Okay, and this should look pretty good now, right? And hopefully it's jumping out at you why this is good. And the reason for that is because we can use our A-level maths trig identities. Okay, so tan squared theta plus 1, well that's just simply sec squared theta. So what we actually have now is the square root of 9 sec squared theta. And then we can square root that. So this is the integral now. Of the square root of 9 sec squared theta, which will just give me 3 sec theta. So that's good. Now we just need to simplify this. So simplifying all this now, all you're going to get left with is the integral of a half sec theta, and this is with respect to theta, so d theta. Integrating this now, nice and straightforward, just the integral of sec theta. You can take the half out to the front if it helps. So this is just going to be a half ln. In the bracket here, I'm going to have sec theta plus tan theta plus tan theta. Now, we can use the given forms in the book because we know it's got to be a hyperbolic sine inverse, b of x, okay? And we can use the formula book for maths, which gives you the forms of what this is going to be. So using that, I'm just going to sub everything in now of what will be appropriate. So it's going to be a half ln, okay? It's going to be 2x over 3 because it's a half ln tan theta plus sec theta here. So if I just put this in first, I'm going to get to the form a little bit, but first I'm just replacing what we've got here. We've got sec theta and we've got tan theta, but we know tan theta is 2x over 3. So this is 2x over 3. 2x over 3 and sec theta, well, that's going to be the square root of tan squared theta plus 1. Okay, so if I try and get all this down, plus the square root of sec, the square root of this here to give me just sec theta, so it's going to be the square root of 1 plus tan theta, which we know is our tan squared theta, which is 2x over 3 squared. So I'm going to write it all down. 2x over 3 all squared, like so. Okay, so we'll hopefully just get there with enough room. But this now is in the appropriate form for hyperbolic sine inverse. If you look in your formula book, you'll see that this is exactly in the form that we need. So just writing that out as it is now. Therefore, we're going to obtain that u is going to be equal, I should call it probably theta in my case. Theta is going to be equal to a half hyperbolic sine inverse 2x over 3 plus c. And there we have it, that's part A done. So there's some tricky integration going on there. That part's not quite as straightforward as part B, but it's necessary to get to part B. So if we clear that, let's jump straight back into this now with part B. So part B, we have to find in exact form, in terms of natural logarithms, the mean value of f of x over the interval 0 to 3. So to find this now, this is going to be the integral of, so if I do it, so it's going to be the integral of b to a, or a to b, of f of x dx, and on the outside here, you've got 1 over b minus a, so 1 over b minus a. So, if I had to do that now, what will that give me? Well, b, so my b here is going to be 3, that's your upper limit here of the interval, and your a is your lower limit. So it's going to be 1 over 3 minus 0, so 1 over 3. In here now, we've got f of x. We've expressed it in this form. So it's the very last line that I just wrote, so it's going to be a third of half hyperbolic sine inverse minus 1, and it's of 2x over 3. So 2x over 3. And I'm doing this again between the limits b to a. So that's going to be 3 to 0. And now we just got to evaluate this for the, the last mark. So this is going to be a third of a half of hyperbolic sine inverse. Now, if I'm putting 3 in here, I'll get a value. If you put 0 in here, you're not going to get a value, right? Because hyperbolic sine will be 0 when x is 0. So that's not going to give you any value there. So I'll put this in now. It's going to be 2 times 3 over 3. Like so. Keep simplifying this now. This is going to be a third. And notice now we can use the hyperbolic sine and put it in the logarithm form because it wants it in terms of logarithms. So just like the last line of wicking we had where it was a half ln 2x over 3 plus the square root of 1 plus x 2x over 3 all squared, we're going to do that again. So put it in that form. It's going to be a half ln. In the bracket here now, it's going to be 2 plus square root of 1 plus 2 squared. Because it's 2 times 3 is 6, divided by 3 gives me 2. Okay? And then evaluating all this, I'm just going to get 1 over 6, a third, times a half, 1 over 6. 1 over 6 ln 2 plus root 5. And there we have it. That's part B, fully complete for question 3. Moving on to question 4 now, we have a question here dealing with complex numbers and more specifically the Moivre's theorem. Okay, so it's quite a good question. I do really like this question. It's split up into 2 parts, and the first part is just asking us to show that these series can be added together because they are both infinite series C and S, and they're defined by C being equal to cos theta plus a half cos 5 theta plus a quarter cos 9 theta and so on, and then S is equal to sine theta plus a half sine 5 theta, that's a mouthful, plus a quarter sine 9 theta, and then so on again. Okay, so part A just asks us to show that C plus is is equal to 2e to the I theta divided by 2 minus e to the 4i theta for the first 4 marks. And then part B just asks us to hence show that s is equal to this equation here. Okay, so let's have a go at it. So part A, so let me just put my pen on. So part A. So we're adding together c plus is. So c plus is. Well, if we're adding these two series together, so my first term would be cos theta plus I lots of s, so I sine theta. So let's write that down. So it's going to be cos theta plus I sine theta. Okay, so that's my first term. Next term would be a half cos phi theta plus a half of I sine phi theta, but we can factor out the half, right? So what I'm going to have here is plus a half, and then I'll have cos phi theta plus I sine phi theta. Okay, and again we'll just do it once more just to show the pattern. This is going to be a quarter. We can factor that quarter out again, just like we did here with the half, and then we're going to have cos 9 theta plus I sine 9 theta. Okay, and this is going to go on infinitely, right? So it's going to be plus and so on. So we're not going to bother writing out any more terms. Now we need to think about getting this into this form here. So how do we do this? Well, I can use Euler's formula, right, to change how we write this. Cos theta plus I sine theta. Well, that's just going to be e to the I theta. Okay, this bit here is the same as this here. Okay, so cos theta plus I sine theta we can rewrite as that. So let me just write that over here. Just to make it clear. Okay, so that's where that's come from. So now I'm just going to do the same like we've done here. So it's going to be a half e to the 5i theta. And again here, this will be a quarter e to the 9i theta. So let me just write them down. So that's going to be a half to the 5i theta. And then again, plus a quarter e to the 9i theta. So again, this will carry on infinitely. But notice this is a special kind of pattern, right? This is a geometric sequence. Notice you've got e to the I theta plus a half e to the 5i theta, then a quarter e to the 9i theta. So what's the common ratio here? Well, my common ratio are, well, that's just going to be a half, because each time it's times by half, a half, a quarter. Next one would be 1 over 8. So it's a half my common ratio. And what's my first term? My first term will just be e to the I theta. Oh, sorry, I forgot the r. I got a bit carried away. It's a half. But don't forget, my other part to this is my e term. So it's going to be a half e. And then what happens with the powers? So at each point, it's increasing by 4i theta. Okay? So 4i theta. So it's not just a half. I got too carried away, then I jumped straight into my my first term. So don't forget your e to the 4i theta. So if this is a series now, and it's an infinite series, then I can sum this to infinity, right? So using. So this is going to be, if you remember the formula, it's going to be a over 1 minus r. So using this now, my sum to infinity, that'll be a over 1 minus r, so let's write it down again. So that's going to be my first term, a, that's going to be e to the I theta, all over 1 minus r, so 1 minus a half e to the 4i theta. Like so. Now notice they want 2e to the I theta over 2 minus e to the 4i theta. So how do we get it in that form? We've just got to times through by 2, right? Gets rid of that half there, that fraction of 1 over 2, and it gives us the correct form for the answer. So therefore, times through by 2 now, and this will give us c plus is being equal to 2e to the I theta all over 2 minus e to the 4i theta. That's an I there, believe it or not, 4I theta. And there we have it. So we've got 2e to the I theta over 2 minus e 4I theta. Okay, so we'll just quickly clear this. So that's part A done. Now we've got to jump into part B. So part B, we've got to hence show that s is equal to 4 sine theta plus 2 sine 3 theta over 5 minus 4 cos 4 theta. Okay, so how do we do this? So what it wants is just s. So notice this is c plus is. You could also think of this as kind of like our form of a complex number. So x plus I y. This is the real part. This would be your imaginary part. So we could just call it im. So we just want the complex form here, or the imaginary part. So how are we going to do that? Well, we're going to have to times this part here, our c plus is, through by something. And very common with complex numbers and surds, you're going to times through by the conjugate. So your conjugate here will be 2. So if I just call it conjugate, try the word out for this one. So keeping it in terms of exponentials, it's going to be 2 minus e. So be very careful how you write this conjugate out. It's just going to be 2 minus e to the minus this time, minus 4i theta. Okay. So if that's the conjugate, all I've got to do is times top and bottom by the conjugate. So what will that give us? I've got 2e to the I theta times 2 minus e to the minus 4i theta. Again, do the same with the denominator. Times this again, so this will be by the same as my numerator in my second fraction. 2 minus e to the minus 4i theta. Again, that's an I. It just isn't coming out with my fraction line. So it's a bit messy, but hopefully it's still clear what we're doing so far. So times in through now, doing the numerator first. So if I've got 2e to the I theta times 2, that'll give me 4e to the I theta. 4e to the I theta. 2e to the I theta times minus e to the minus 4i theta. So be very careful here. This will give us minus 2e. So be careful with your power now. If you've got I theta and then you times it by minus 4i theta, in total now we have minus 3i theta. Okay, so we're adding the powers. My denominator, if we work that out, 2 times 2, that'll be 4. 2 times minus e to the minus 4i theta. So I'm going to get minus 2 lots of that. So minus 2e to the minus 4i theta. And then I've got minus e to the 4i theta times 2. So again, I'm going to have minus that. And then finally, we've got minus e to the 4i theta times minus e to the minus 4i theta. So timesing these together now, we're technically going to cancel out, okay? So it'd be kind of like your I squared here. Or minus I squared minus minus 1 is essentially what we're going to get here in principle. So this will be plus 1. Now we just need to simplify here. And what I'm going to do is I'm going to change back from my exponential form here and get it in terms of sine and cos from my c and my s. Okay, so if I do that, hopefully I might have just about enough room. Doing the numerator first, so 4e to the I theta. Remember, we wrote down e to the I theta. That's equal to cos theta plus I sine theta. Okay, so we just need to convert all these now. So that's going to be 4 cos theta plus 4i sine theta. So that's the first part. And I'm going to do minus 2 cos 3 theta this time. Cos 3 theta. And then plus 2i sine 3 theta. Okay, so that's my numerator done. So this is going to be quite long, this last line of working. Dealing with the numerator now. So we've got 4 plus 1, so hopefully that's nice and straightforward. For a further maths A-level student, that'll just give us 5. I've got my minus 2e to the minus 4i theta. So what will that give me? Well, that'll give me minus 2 cos 4 theta. Okay, minus 2 cos 4 theta. I'm going to get plus 2i sine 4 theta. I'm just writing everything out here. I'm going to get a minus 2 cos 4 theta again. And then finally, I'm going to also get a minus 2i sine 4 theta. Minus 2. So let me just undo that. So minus 2i sine 4 theta. Again, this is very easy to make a mistake, so just take your time with this. So, simplifying here, I can now look at my denominator. So I've got 5 minus 2 cos 4 theta minus 2 cos 4 theta. So, that'll give me 5 minus 4 cos 4 theta. I've got a 2i sine 4 theta and a minus 2i sine 4 theta. So they will cancel, so that's fine. The denominator is perfect. And here now, I've got 4 cos theta plus 4i sine theta minus 2 cos 3 theta plus 2i sine 3 theta. So, how do I get the last bit of the answer here? S. Well, think about what's going on here. Your denominator will always be 5 minus 4 cos 4 theta. But on your numerator here, this is split up into the real parts and the imaginary parts. Now for S, we technically only want the imaginary parts. What we've actually got here, if I write over here, what we're dealing with here is 4 cos theta, so just write my real parts, minus 2 cos 3 theta. Okay, that's my real part. That's over 5 minus 4 cos theta. And I've also got the imaginary part, plus, and my imaginary part is the parts here. So it'd be 4 sine theta plus 2 sine 3 theta. And it'd be over the same denominator, right? It's just a common denominator. So we just want the S. This here, this is C, which we don't want. We just want to show that S is equal to this. So S is going to be equal to your imaginary part. So it's going to be 4 sine theta plus 2 sine 3 theta. And there we have it. We've shown that S is equal to 4 sine theta plus 2 sine 3 theta all over 5 minus 4 cos 4 theta. And there we have it. That's question 4 fully complete. Moving on to question 5 here, we have quite a tricky question, and it's to do with differential equations, right? So it's a differential equation modelling question in context. So it's nothing particularly exciting. It's about a diving board and measuring this using this differential equation. So like I said, pretty boring, but it's part of the question, so we've got to do it. So let's start right at the beginning. Part A just asks us to find a general solution of the differential equation for 2 marks, okay? So should hopefully be quite straightforward for 2 marks, so let's have a go at this. So part A. So to find a general solution for this, as this is a second order differential equation, I'm going to model this now using my auxiliary equation. So that's going to be 4m squared plus 4m plus 37. This is going to be equal to 0. So you can always tell if it's in this form where it's like a multiple of your second order, so your second differential, plus 4 lots of the same differential here, and then plus 37 lots of like the function that you differentiated, then you can model it using an auxiliary equation like this. Now we need to solve this. So straight away this jumps out to me that it's not going to factorise, so I'm going to have to use the quadratic function, okay? So let's just do that underneath. So m is equal. So using my quadratic function, so you know this is GCSE, should hopefully be nice and easy. Minus 4 plus or minus. So it's going to be 16 minus 4 times by 4 times by 37. Okay. And this is all going to be over 2 lots of a, which is 4, so 2 times 4 giving me 8. So I'm just going to jump straight away to solving this. I won't show all the preliminary steps because it's nice and easy. This is going to give me minus 4 plus or minus the square root of minus 576. So we're going to have some complex roots here. Minus 576 over 8. And then simplifying that, that's going to give a half, minus a half even, plus or minus 3i. Okay. So we've got that here. That's my m. So now we just need to write the general solution. So, because in terms of h, Therefore, h is equal. Remember, for this form now of a conjugate complex root like this, we write as h equals, so it's going to be e. So the first one, so minus a half t, times by a cos 3t, and plus b sine 3t. Okay, so that is my general solution for this one. So that's the first 2 marks there. Let's have a go at part B now. Okay, so part B, it's telling us that when t is equal to 0, so when t is equal to 0, the end of the diving board is 20 centimeters below E. So that's the position of the end of the diving board when it is at rest in its equilibrium position. So if t is equal to 0, what that's telling us is that h must be minus 20. Okay, so it's 20 centimeters below E. Okay, so minus 20. Well, if I know this, t is equal to 0 and h is equal to minus 20, all I've got to do now is use my general solution to obtain a value for A, and then using A we can then work out B as well. So what that's saying is that minus 20 is equal to e to the minus a half times 0, so that's going to be e to the 0, times a cos 0 plus b sine 0. Okay, well, this is still minus 20. That e to the 0 is just going to be 1, so it's going to be a cos 0, which is just going to be a, and that b is going to cancel. Okay, so I get minus 20 is equal to a, or I can just say a is equal to minus 20. Okay, so hopefully that's clear so far how we've done that. We've just got a is equal to minus 20. So I've just subbed in t is equal to 0 and h is equal to minus 20, like we've been told just before part B here. Okay, so I can now get b, but to get b, I'm going to have to differentiate this, right? Because I'm never going to get a value here because my b is always going to cancel. And we've also been told that it's moving upwards with a speed of 55 centimeters, okay, per second. So if it's moving upwards with a speed, we're talking about velocity, and we know the displacement here, that's h. So if I differentiate h, I've then got velocity, okay? So just going back to your basic mechanics, the derivative of velocity, displacement will give me velocity. So doing this now, so you will need a product rule for this. Obviously I'm not going to show this as well because it's going to be quite long if I do, but I'll show you what you should get once you've done product rule, okay? Because you've got e to the minus a half t, and then you've got this bracket here. So split that up and then differentiate. So what you will get is minus a half e to the minus a half t. Again, you're going to get your a cos 3t, but we know a is minus 20, but we'll just keep it as is for now. A cos 3t plus b sine 3t plus e to the minus a half t again. And this time it's going to be minus 3a sine 3t, so sine 3t. So it's that long now I've actually gone off the paper. Oops, I shouldn't have closed the bracket just yet. Sine 3t plus 3b cos 3t. So 3b cos 3t. Okay, so this question's quite long and it's very easy to make a mistake, so I'm just going to try and take my time just so we don't make any mistakes here. So that's my differential now. That's my speed. So we can now use the fact that when t is equal to 0, okay, the differential here, so dh by dt, is equal to 55. That's what we've been told. The speed is equal to 55 meters per second, okay, or centimeters per second. So using this now, I can work out that 55 is going to be equal, so minus a half e to the minus half t, so that's going to be 1 again, so minus a half minus 20 times 1, so minus 20. So my first bit here, this b sine 3t will cancel, so I'm going to get minus a half. It's going to be minus a half of minus 20, okay? It's going to be minus a half of minus 20 here, because my a is minus 20 cos 3t, so it's going to be minus half of minus 20, like so. And then I'm also going to get plus, so this again will be 1, this sine 3t will cancel, I'm going to get 3 lots of b cos 3t, okay? So that's going to be 3b over here, because cos 3t is just 1, so I get plus 3b. Simplifying this, I'm going to get 55 is equal to 10 plus 3b, so therefore 3b is going to be equal to 45, so therefore b is going to be equal to 15, right? 45 divided by 3, we get 15. So what I'm going to quickly do is just clear all this, and then we'll write out our new h. So what we've got now, if I just do it up here, we've got that h is going to be equal to e to minus half t times 15 sine 3t. So all I'm doing now is putting my b and my a into the equation. Minus 20 cos 3t. So we've got h. All we need to do now is set h equal to 0, and we can then solve this for t. Okay, so this next bit is quite tricky. There's a couple of different ways you can do it. My way is probably a bit trickier than other ways, but as long as you can get a final solution at the end, then that's absolutely fine, okay? So what I'm going to do now is I'm going to set this equal to 0. So I'm going to run out of room again, but just to make it clear how we're actually doing this. So I'm going to have minus a half e to the minus a half t. And then I'm going to put my a and my b in, so it's 15 sine 3t minus 20 cos 3t plus e to the minus 0.5t 60 sine 3t plus 45 cos 3t. Now this is equal to 0, okay? So that is equal to 0, okay? So let's have a go at this now. So this was my dh by dt. So if I set this equal to 0 now, so we're setting this equal to 0, sorry, not h. So if I set this equal to 0 now we just got to solve and get a value for t. Okay, so like I said, there's a couple of tricky parts here, but again, you know, take your time with it, and we should get there. So the first thing I'm going to do here is take across this minus part here onto the other side. So I'm going to have this here being equal to this, but make it positive, okay? So I'm going to have e, so let me just undo that. So it's going to be e to the minus half t So I'm going to set this equal to this side now, okay? So 0.5 e to the minus half t 15 sine 3t minus 20 cos 3t. Okay, now we need to look at simplifying this. What I'm going to do first, I'm going to times through by 2, because this is a half. So I'm going to times through by 2. So what that's going to give me is that's going to give me 2e to the minus half t. And then I'm just going to rewrite all this now. Plus 45 cos 3t. So from here to here, I'm just timesing by 2. So if I just do that here, times by 2. So that's going to be equal to e to the minus 0.5t 15 sine 3t minus 20 cos 3t. Okay, now we've got e to the minus half t on both sides. Now what I can actually do here is divide through by this e to the minus half t, because e to the minus half t can never be equal to 0, so it will never cause any issues with division. I can actually divide both sides by e to the minus half t. So I'm going to do that now. So my next step, I'm going to divide by e to the minus half t. Okay, so we're going to divide through this. So what that's actually going to leave me with now, and I'm also going to divide in the same step, I'm going to divide by cos 3t, right? Because what I want is here, to get this into a term that I can just work with one single term. Well, if I divide through both sides by cos 3t, I'm going to get this in terms of tan, right? 6, so cos sine over cos will give me tan. So what I'm actually going to get now, all in one line, is 2 lots of 60 sine 3t plus 45 cos 3t. Like so. And this is all going to be over cos 3t. Okay, so it's going to be all over cos 3t. This is going to be equal now to 15 sine 3t. Again, timesing through by this e to the, dividing through by this e to the minus half t, it'll disappear. So I'm going to get 15 sine 3t minus 20 cos 3t. Like so. And again, this will be divided by cos 3t. So, simplifying this now, what I'm going to get left with is 120. So I'm timesing through by the 2, and then I'm dividing both sides by the cos 3t now, so I'm going to perform that. So I'm going to get 120 tan 3t, and then obviously 45 cos 3t over cos 3t will just give me plus 45. Okay, so I get positive 45. That's going to be equal now to 15 tan 3t, 15 tan 3t, minus 20. Simplifying this now, what I'm going to get left with here is 105 tan 3t, so I'll do it over here. I'm going to get 105 tan 3t. That's going to be equal to minus 110. Minus 110. So therefore, tan 3t is going to be equal to minus 110 divided by 105. Okay. So, let me just quickly clear this just so we can finish this question. So make sure you've got this down, guys. Tan 3t is equal to minus 110 over 105. So if I write this down, this would simplify to tan 3t. Well, that's going to be equal to minus 22 over 21. Okay. So now we just got to solve this. So, solving this now. Well, if I take tan inverse of both sides, so tan inverse of both sides, minus 22 over 21. Well, that will give me, it'd be minus 0.808. It goes on for quite a bit, 6, 4, 9, and so on. But I'll just write it like that. But we clearly can't have this as our t value, right? T must be positive. So, I need the next solution. So, to get the next solution, I need to add pi to this. So, therefore, this will be 3t will be equal to pi minus 0.80869. Make sure you're in radians here, guys. So this is going to give me, and then what I'm going to do is I'm going to divide through by t. So t is going to be equal to this divided by 3. So divide by 3 here. So what you'll get for t is 0.7782 3 decimal places here. And there we have it. That's our t value for this question. So that's the maximum vertical displacement at the end of the diving board. So that were a lot of marks, and it was quite tricky and very easy to trip up with. And then part C, just for the last 2 marks, asks you to comment on the suitability of the model for large values of t. So kind of a clue there with the large values of t. Well, if you put a large value into your t here, what's going to happen? Well, plug in a large value into t now. Well, we've got this e to the minus a half t, right? So, for example, h equals e to the minus a half t. And then blah, 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 whatever's in this bracket. But we don't even need to worry about this bracket. Think about what's going to happen with this. Well, what I'm going to say as t tends to infinity, what will happen here? Well, if I put a really large value of t in here, this is basically going to be the same as 1 over e, or the square root of e here now. So, if you put a large value in, what you're going to get is that this tends to 0, okay? This will tend to 0. So, what that also means is that h must also tend to 0. So, as t tends to infinity, h tends to 0, okay? So, as t gets very large, h gets smaller and smaller, or in other words, it basically becomes 0. So, what we can say about this now is that this is a suitable model, okay? So, therefore, model is suitable. It is suitable because, like we said here, as t tends to infinity, h tends to 0. It's what we'd expect, right? The board will return to its normal state. So, board returns to a state of equilibrium. So I hope I'm spelling this okay. And there we go, that's it. We just got to say that for the 2 marks. And there we go, that's question 5 fully complete. Moving on to question 6 now, we have a question here which is in relation to complex numbers, and more specifically complex numbers in terms of geometry. Okay, so we're given this complex number here, 6 plus 2i, and this is in terms of an argon diagram. Okay, so these are the points A, B and C, where this is the point A. The other 2 points are the other vertices of an equilateral triangle with its centre at the origin. And then part A just jumps in straight away asking us to find the other points B and C. So I really like this question. It's certainly not a walk in the park, but it challenges you to think about what's actually going on. So let's jump straight into this and have a look and see if we can solve it. So 6a, what have we actually got here? So we've got the complex number 6 plus 2i, and we're asked to find the other vertices, and its centre is at the origin. Okay, so let me just draw an equilateral triangle over here for now. Okay, so if you've got an equilateral triangle, if this is my vertex A, this is B, and then this is C. If I rotate this 120 degrees counterclockwise, what would happen? Because we've only got one complex number here, one vertex of this triangle. We need the other 2 vertices. So how are we going to get that? Well, it's important that it's an equilateral triangle with its centre at the origin. What it means is that we can rotate this equilateral triangle and we can obtain the other vertices. Okay, so this point A here, so if we rotate it 120 degrees counterclockwise, this is what we'd get. So we'd get A here, my C would go up here, and then my B would be here. Okay, so we're going to use this fact here that we can rotate. Okay, so it's looking at rotations involving complex numbers. So what we've got, if we just quickly draw it over here, or what we've got currently, so kind of make sure yours looks a bit neater than mine. Mine's a bit rough. We've got the first point here, so it's going to be 6 plus 2i. So let's just say it's there. Okay, so that's 6 plus 2i, so that's the point A. We need to work out the other points B and C. So what we're going to need to use is the rotation matrix. So the rotation matrix that will be equal to, so remembering this will be cos theta minus sine theta, and then cos theta. Okay, and remember we're rotating this 120 degrees, and then to get the other point we then need to rotate by 240, or you could rotate your last one that you worked out again by 120. Both will give you the correct answer. So if I write down my rotation matrix, and don't forget we're going to rotate this, we're rotating 6 plus 2i. Okay, so that would be times by 6 and 2. Okay, so cos theta minus sine theta and cos theta. All we need to know is put our theta in, which is 120. So what we're going to be doing now is cos 120 minus sine 120, sine 120, and then cos 120 times by 6, 2. Okay, because this is our complex number 6 plus 2i. Now I can write these in terms of their exact form here. So this, nice and easy, cos 120, that'll be minus a half. My minus sine 120, that'll be minus root 3 over 2. Sine 120, root 3 over 2. So I'm kind of running out of room, I've done this a little bit too big. And then finally, again, minus a half. So that's my exact form. Again, times by 6, 2. So don't put this on your calculator because we want to keep it in exact form, because notice in the answer, or in the question, sorry, it asks us to give the answer in the form x plus iy. Okay, so we need this in its exact form here. Well, times in this now, what we're going to get? Well, this, so I do this row times this column. So minus a half times 6, so that would be minus 3. So I'll put this as my upper element, so that'd be minus 3. And then I've got minus root 3 over 2 times 2, so I'm just going to get left with minus root 3. Minus root 3. Okay, hopefully this is nice and easy. Again, now doing the bottom row times this column. So root 3 over 2 times 6, so I'm going to get 3 root 3. Okay, so 3 root 3. And then finally, if I do minus a half times 2, I'm going to get minus 1. So that's what I get left with. Now, this is my real part, this will be my imaginary part. So writing it in the form x plus iy, this will just simply be, just going to be minus 3 minus root 3 plus 3 root 3 minus 1 lots of I. And there we have it, that's one of our other vertices, that's probably b, if we call it b, it doesn't matter which one we call it. And then finally, we're going to do the same again, but instead of 120, we need to do it with 240, okay? So it's going to be cos 240 minus sine 240, sine 240, cos 240. Again, we're going to times it by 6, 2. Doing this now, again, write this in exact form. This will be minus a half. This time now, this won't be negative, but it'll be root 3 over 2. This one will be negative, minus root 3 over 2. And then this will be minus a half again. Okay, so that's good. And then we're going to times it by 6, 2. And simply doing this again, what we're going to get, so we're going to get minus a half times 6, so that'll be minus 3. So minus 3. Root 3 over 2 times 2, so I'm just going to get plus root 3. Okay, and then doing the imaginary part here, minus root 3 over 2 times 6, so I'm going to get minus 3 root 3. So just be careful with your signs. Minus 3 root 3. And then minus a half times 2, I'm just going to get minus 1. So this now, if we put it in this form here, x plus iy, so we'll do it over here. So in the form x plus iy, this will be minus 3 plus root 3. Right, so plus minus 3 root 3 minus 1 lot of I. And there we have it. That is the correct form for my two vertices B and C. Okay, so we've got this bit of information now. What I'm going to do is I'm just going to quickly clear it, and then we'll jump on to part B. So, part B, what we've got to work out now is the area, the exact area, of the triangle DEF. And DEF, that is represented by the points D, E and F, which are the midpoints of the sides of the triangle ABC. So if I just draw a rough sketch now, again, this isn't going to be perfect. I'm pretty bad at drawing. I was never good at art, so just a rough sketch. Okay. Just to help illustrate what's going on here. So we had our first one, this was 6 plus 2i, we'll call it there. That was the point A. What I've also got is my other 2 points. So I've put these in on my calculator and already worked them out. But my minus 3 minus root 3 plus 3 root 3 minus 1i, this would be roughly up here. And then my other solutions, this would be my, which one would that be? That would be my minus 3 plus root 3 plus minus 3 root 3 minus 1. That's going to be down here. So that would be about here. Okay, so again, it's nothing perfect. And clearly, like it says in the original question, the centre should be at the origin. It's probably going to look slightly off of mine, but it should be in reality. So I'll just draw it. Okay, that's terrible. Let me just undo that. Let's show you if we can get this right. Okay, that'll have to do. Okay, my triangle's pretty bad. Believe it or not, this is supposed to be an equilateral triangle. We'll just say that's it there. Okay. Just to illustrate the point of what's going on. So, my midpoints now will be here, say, here, and here. So what we're actually looking for is the area of this triangle here. This one in the middle. Okay, that's what we want. We want the area of that there. So we say that's D, that's E, and that's F. We want this area here shaded. So, how do we do this? Well, there's actually quite a lot of ways you can do this. You can do the shoelace method if you've ever come across that. It's quite a nice way to do this question, but it's not a common method. The way I'm going to do it is because it's an equilateral triangle, I'm going to use the formula here that you may be aware of, which is A equals root 3 over 4 a squared, okay, where a is the length of one of my sides of this equilateral triangle. Another way you could do this would be to use a equals a half ab sine c, so just meet your trig. Now obviously this formula here is derived using this, so it's whichever equation you're more familiar with. This one's easier to work with, so if you've come across this and you know how to use it, which is pretty simple, it's just using the length of the equilateral triangle, then I'd just use this. It makes life really easy. So, how do we work out a? Well, we need to work out the length from here to here. So, this is 6 plus 2i, so 6 plus 2i. This one here, this was the one that I wrote down as, so it was minus 3 minus root 3 plus, in bracket, 3 root 3 minus 1i. Okay, so I want to work out the length now from here, from A to this point here, which we'll call B. Okay, so how do I do that? Well, nice and straightforward. We're just going to use the length formula. Okay, so this will be, so A to B, of the length AB, well, that's going to be equal to the square root. So it's going to be 6 minus this whole expression and then square the full thing. So let's try not to make a mistake. So it's going to be 6 minus 3 minus root 3 all squared. Okay, like so. Then we're going to add, and then we're going to take off the imaginary part. Okay, so it's going to be plus bracket 2 minus, and then this part here. So it's going to be minus bracket 3 root 3 minus 1 all squared. So that'll give us this length here, which we can call it A. So I've already put this all into my calculator, but if you do this correctly, what you should get is the square root of 120, okay? Which you can write as 2 root 30 if you want. But using this formula, it's probably just easier to keep it as root 120, okay? So plug in this now, so this is my A. Plug in my A into this formula here, we can get an exact area of the triangle DEF. So root 3 over 4 times A squared, which A is the square root of 120, the square root of 120 all squared. Well, this now will be the square root of 3 over 4 times 120. So square root of 3 over 4 times 120. This now will cancel 120 over 4, so that'll give me 30. So this is 30 lots of root 3. Now, let's not get carried away. We haven't quite finished yet. And the reason why is because this length here, this A, is for my triangle ABC. Well, we've got these points here, the midpoints. Well, notice here now, we've split this up into a triangle. And it's in the middle of this original triangle we're working with. So, this is going to be a quarter of my full triangle. If any of you are fans of The Legend of Zelda, you'll notice this is like the Triforce. So we've got this triangle in the middle here. This is a quarter of my original triangle. So we need to now divide this by 4. Okay. So 30 root 3 over 4. Well, that'll just cancel to 15 root 3 over 2. And there we have it. That's the exact area of DEF. So area of DEF. And there we have it. Like I said, you could have done a few other methods, so you can use shoelace, you can use half AB sine C. There's lots of different ways of doing it. So quite a nice question overall, but there we go, it's fully complete. Moving on to question 7 now, we have a question here on 3x3 matrices, and then this is in terms of vectors as well. So a bit of a mixed question here, and it's a decent question. You know, there's a couple of little tricky parts to it, but overall, quite a nice question. Okay, so let's jump straight into it. So part A, we have to find the values of K for which the matrix M has an inverse. So we've got this matrix M, and we're told that K is a constant, okay? So, if M has an inverse, what that means is that the determinant is not equal to 0, right? So, all I need to do is expand along this middle row here and find the value of K that would make it equal to 0, and then basically K would be any other value, okay? So, let's have a go at doing that. So if we expand along this row, well, if I expand along this row, well, we start here, and I'd have to delete this row as well. So we delete this column, sorry, and then this row. So all I get left with is minus 1, 1, 2, minus 1. Okay, so and my cofactor will be 3, but remember it goes positive, minus, positive, minus. So my first one's going to be minus. So what I'm going to actually have here is minus 3. Oops, let's change it to pen. So it's going to be minus 3. So minus 3. Lots of the determinants, like we said, minus 1, 1, 2, minus 1. So we're splitting it up now into a few separate 2 by 2 matrices here. We can work out those individual determinants. Now we're going back up here, deleting this row and this column, and my cofactor will be k, and this time it will be positive. So I'm going to get plus k lots. My determinant now is going to be 2, 1, 3, and then minus 1. We're going to have to work out the determinant of that. And then finally, going back up here, we want this row again, and then this column. We're deleting those two. So I'm going to get 2, minus 1, 3, and 2. They're the only 4 values that are left. So it's going to be minus 4 this time again. Minus 4. So it's going to be 2, minus 1, 3, and 2, like we said. Okay, so now I just need to work out these individual cofactors and set this equal to 0. So let's work this out now. So it's minus 3 lots of, so minus 3 lots of, minus 1 times minus 1, so that's 1 minus 1 times 2. So that's going to be 1 minus 2, so that's going to be minus 1 in there. I've then got plus k lots of this, so plus k lots. 2 times minus 1, so that's going to be minus 2, minus this 3 here. So I'm going to get minus 5 times k, so that's going to be k lots of minus 5. So we'll just simplify in a second. And then I'm going to have minus 4 again. 2 times 2 is 4, minus 3 times minus 1, so it's going to be 7 in total. Okay, so I'm going to get minus 4 lots of 7. And this is going to be equal to 0. Now we're just going to solve for k. So minus 3 times minus 1, I get 3. K times minus 5, I get minus 5 lots of k. Minus 4 times 7, I get minus 28. It's equal to 0. Now I'm going to simplify this. So I'm going to get 5k is going to be equal to, oh sorry, this is equal to minus 25. So therefore, k, now remember we don't want this value, so therefore k cannot be equal to minus 5, cannot be equal to minus 5. That's the only value that we can't have. So any other value will give us an inverse. Okay, so that's part A done. So we'll just quickly clear all this. Let's jump on to part B now. So part B, what have we got to do? Well, we've got to find, in terms of P, the coordinates of the point where the following planes intersect. Okay, so we're looking at these set of vectors here, these set of equations. Notice this is identical to this. So it's 2 minus 1, 1, 2x minus y plus z. Okay, so that's my first line of my matrix. I've got 3 minus 6, 4, 3 minus, well, that was k there, but we'll call it minus 6, 4, and then 3, 2 minus 1, 3, 2 minus 1. Okay, so this is going to help us now, this m here. And then for this question, make sure you're using your graphical calculator. It will come in very handy. You don't need it, but it just saves you a lot of time. So what we're saying here is we're going to find a set of coordinates. So if I call it x, y, z, x, y, z, like so. Well, that's going to be equal now to the inverse of m inverse, times by this vector here, p1, 0. So doing that will actually just give me the answer that I need. So m inverse times p1, 0. And I'll get my answer. So m inverse now, well, what I'm going to work this out is just using my calculator, but where k is, make sure you replace it with minus 6, okay? So you're going to put this on your calculator and then work out the inverse of it. So you do the matrix times to the power of the inverse. So if I put that on my calculator, what you'd actually get here is m inverse. I'm going to factor the 1/5 out, but on your calculator it will give it as, like, for example, minus 2 over 5, but I've factored it out as 1 over 5. So 1 over 5, 3 by 3 matrix. So it's going to be minus 2, 1, 2, 15, minus 5, minus 5. And then finally 24, minus 7, minus 9. Okay, so that's my m inverse. Now what I actually need to do is times it by p, 1 and 0, okay? So obviously you can't do this on your calculator because this has a constant in it. Well, it's got this variable, sorry, it's got this p, so we can't put it in on the calculator. So I'm going to now times m inverse by p, 1, 0. So that's going to be 1 over 5 on the outside again. Minus 2, 1, 2. Minus 5, 24. Minus 7. So I'm just writing it all out again. Now I'm going to times this by p, 1, 0. Okay. So expanding along the top, well, if I multiply this through, now it's just going to be minus 2 times p, it's minus 2p, 1 times 1 will be 1, and 2 times 0 will be 0. So that's going to be, my first value will be, so I'm going to keep the 1/5 on the outside just yet, so it's going to be 1/5 of minus 2p like we said, plus 1. Doing the next one now, so 15 times p, I'm going to have 15p minus 5. So 15p minus 5, but hopefully this is really straightforward multiplication. 15p minus 5, and then finally 24 times p, I'm going to get 24p minus 7. So now it's all we have to do now is times times it by 1/5. I'll divide it by 5. So what I'm going to do is I'm just going to write them underneath. We should have enough room, I hope. So what this is going to give, it's going to be minus 2p plus 1 divided by 5. And remember, write this as coordinates now. So minus 2p plus 1 over 5. I'm going to have 3p minus 1. Oops, let me just undo that. 3p minus 1, and then finally we're going to have 24p minus 7, 24p minus 7, all over 5. And there we have it. So that's the coordinates there of the point where the following planes intersect. Part C, let's have a look at what we've got to do here. So for part C, we have to find the value of k for which the set of simultaneous equations can be solved. So this is actually quite straightforward. A couple of ways you can do it, but the easiest way that jumps out at me is looking at how these equations are formed. All we can do is just substitute a point in, right? So if I say, so for part C, if I say let x equal 2, so let x equal 2. So let x equal 2. So what I'm going to get then is subbing it into my equation 1, the top one, and then equation 3 here. We're going to sub x is 2 into both of these. So that's going to give me 2 times 2, so that's 4. I'm going to subtract it off this side. So 1 minus 4 is minus 3. So I'm going to get minus y plus z is equal to minus 3. Okay, so that's the first equation. Subbing it into here now. 3 times 2, so that's going to give me 6. And I'm going to do 0 minus 6. So I'm going to get 2y minus z is equal to minus 6. Okay, solving these now simultaneously. Really straightforward. I'm going to get that z is equal to minus 12. Z is equal to minus 12. And now just to work out y. Sorry, what you would get first is that you get y is equal to minus 9. I've accidentally wrote down my second solution first. So you get y is minus 9. And then using y is equal to minus 9, you can work out z is equal to minus 12. So we've got our two solutions. All we've got to do now is sub it back into our middle one. And we're going to get the value of q. So if I do that over here, 3 lots of 2, because x is 2, minus 5 lots of minus 9. Just subbing in my y and my z now. So my y is minus 9, and then plus 4 lots of minus 12. What's this equal to? Well, that's going to be 6. That's going to be plus 45, and that's going to be minus 48. Simplifying all that, what we get is that q is equal to 3. Okay, and this will work no matter what value you pick for x. You can do z, you can do y. As long as you do everything else correctly in between, you'll get that q is equal to 3. Okay, so there you go. That's the value for q, which can be solved. And then finally, the very last part, just a 1 marker. It says, for this value of q, interpret the solution of the set of simultaneous equations geometrically. So it's just asking what happens now with this value. Well, what this is saying is that the planes all meet in a line. So the planes meet in a line. Or you can say intersect, so meet. Finally, moving on to question 8. Now the final question is Core Pure 2 exam. We're looking at a question here in terms of modelling, and modelling with volumes of revolution. Okay, so quite a long question. Part A and B are quite nice, and part C and D are quite tricky. So let's jump straight into this. So part A, it just asks us to find the value of k. Now k is used in this equation here, y equals ln 3.6x minus k. Now this equation here models the curve BD. So using this information now and this figure 2, can we extract anything? Well, we know when x is 1, here, when x is 1, what's my y value? Well, that's just clearly 0. So when x is 1, y is equal to 0. Well, we can use that. We can use the equation to obtain a value for k. So when x is 1, y is 0. So what we know is that ln of 3.6 x, but x is 1, so ln of 3.6 minus k, that's equal to 0. So what ln value gives us 0? Well, that's just clearly ln of 1, right? From your A-level maths, ln of 1 gives us 0. So this bit here needs to be equal to 1. So what do we subtract from 3.6 to give us 1? Well, therefore, k must clearly be 2.6. Okay, so k, that's k, believe it or not, my writing's just gone very off there. K is equal to 2.6. So that's part A done. So we just mark that in. Now part B, what's part B asking us to do? Well, part B says find the depth of the paddling pool according to this model. So again, we're using this model here, and we want to know what the depth of the paddling pool is. Well, the depth will be when x is at its maximum, right? 1.18. So all I've got to do is sub 1.18 into my equation. And my new equation, don't forget, will be y equals 1, and it'll be 3.6x, and where the k was, remember we've got a value now, we've got 2.6. So minus 2.6. Okay. And we want to know what happens when x is 1.18. When x is 1.18. Okay, so just subbing that in now. Therefore, y is equal to ln 3.6 times 1.18 minus 2.6. What does this give us? Well, you'll get 0.4995 meters. And there we have it. That's the depth of the paddling pool according to the model, using this equation here for the curve BD. So that's part A and B done for the first 3 marks. So now we jump into part C, where we're looking at some of the trickier maths. Okay, so we just quickly clear this. Part C. So part C is looking at volume. This is where the volume of revolution is applied now, because we're looking at the volume of the water in the pool when the pool is filled to a depth of h meters. So, because we're talking about volume, so that's our y equals here, we're going to be rotating about the y-axis. So we need this in terms of x now, okay? So we're going to have to do some rearranging to get this in terms of x. So if I just do this up here, so to get this in terms of x, well, first thing I'm going to have to do is take the antilog here, so this will be e to the y. That's going to be equal to 3.6x minus 2.6. Now, just add 2.6 to both sides. Or what I might do is just, yeah, so 3.6x, I'm just going to write it this way around. That's going to be equal to e to the y plus 2.6, like so. And then finally, we've just got to divide by 3.6. So therefore, x is equal to e to the y plus 2.6 divided by 3.6. Okay, so we've got it in terms of x now. So my formula now will be v equals, so remember your formula, it'll be pi times the integral. We won't put any limits on just yet, we'll come back to that when we're about to perform the integration. And then it's going to be my x squared, where this is x, so it's going to be e to the y plus 2.6 over 3.6 all squared. So if I write that down, plus 2.6, and this is over 3.6 all squared, and this is with respect to y now. Okay, so the first thing to think about here is that this would be e to the y plus 2.6 all squared, and this would be divided by 3.6 squared. So what I can do is I can take that 3.6 squared out of this. So what that'll give me is v equals, so it'll be pi over 3.6 squared. Okay, that's the first thing I can do to make this a little bit nicer to work with. Now what I've also got, if I do it over here, is I've got e to the y plus 2.6 squared. Well, this is nice, easy double bracket just to expand. So if you expand this, what you'll get is e to the 2y plus 5.2 lots of e to the y. So 5.2 lots e to the y. And then finally you'll get plus 6.76. Okay, expanding this. So what I can do now is write out my full integral. So it'll be the integral of e to the 2y. And then it's just this expression here, plus 5.2 e to the y. Plus 6.76. And this is all with respect to y. So let me just put a bracket around it. dy. So I might run out of room here, hopefully not. But what we've got to do now is integrate this. Now let's think about limits. What it's saying is that this is in terms of h when it's filled to a depth of h meters. So what we know is we're going to start with a depth of 0, nothing's in the pool, and it's going to go up to h. So my limits are just simply 0 to h. Okay, so we're going to integrate this now between 0 to h. So what will I get when I integrate this? So integrating this now, what we're going to get is, I'm going to do this over here just so I've got enough room. So this will be pi over 3.6 squared again, like so. In the bracket now, I'm going to get e to the 2y divided by 2, okay? Because we're integrating e to the 2y over 2 plus 5.2 e to the y, like so, and it'll be plus 6.76 e to the y. Sorry, 6.6, getting muddled up, 6.76 y. There we go. Okay, and this is between h and 0. Okay, so I'm kind of going a bit curved here, but all I've got to do now is plug these limits in here, and we're going to get our value. So I'm just going to do it cleanly across the bottom here now. Hopefully we will have just about enough room. It's going to be a bit tight, but what I'm going to get is pi over 3.6 squared, okay, just like we had here. Plugging in h now, this will be e to the 2h over 2, so this will be in two different parts now. So it's going to be e to the 2h over 2, e to 2h over 2, plus 5.2, so wherever there's a y, it's just going to be replaced with a h, 5.2 e to the h, plus 6.76 h, okay, so that's my first bracket, and then we've got a minus off when it's 0, okay, so it'll be e to the 2 lots of 0, so e to the 0 over 2, so it's going to be minus e to the 0 over 2, e to the 0 over 2, plus 5.2 e to the 0, and then finally plus 6.76 times 0, so that'll just be 0, so that'll be that. So I've already done this on my calculator, but if you perform all this and write out and simplify it, what you'll actually get is pi over 3.6 squared. Okay, so it's like we had at the beginning. We're going to keep it like that, pi over 3.6 squared times e to 2h over 2 plus 5.2 e to the h, like so, 5.2 e to the h plus 6.76 h, and I'll have my minus 5.7 at the very end. And there we have it. That is the volume here of water in the pool when the pool is filled to a depth of h meters. So quite a tricky question there, but it's the most important thing is recognizing that we're about the y-axis when we're rotating it. Okay, so that's part C done. And then finally, let's have a look at part D. So I just clear all this. Let's look at part D here. So we're told, or given the information, that the pool is filled at a constant rate of 15 litres every minute. So it says find in centimetres per hour the rate at which the water level is rising in the pool when the depth of the water is 0.2 metres. So part D. Now, the fact that it says rate means there's going to be some differentiation involved here. And this is technically a connected rate of change question. This used to be on the old Edexcel C4, but it's kind of made its way into the further maths section now. Okay, so if I write up here just so we've got it, we know V is equal to pi over 3.6 squared, again times by e to the 2h over 2, e to the 2h over 2, plus 5.2 e to the h, and then finally plus 6.76 h, okay? So now I just need to differentiate this. If I differentiate this, we're going to get dv by dh. Now, what I actually want is dh by dt. That's what we need. So we need dh by dt. Now, how will we obtain dh by dt? Well, we're going to have to use chain rule, right? That's going to be dh by dv times dv by dt. Okay? And that will give me dh over dt. Okay? So, dh over dv, well, I can obtain that by differentiating v here and then taking the reciprocal. And my dv by dt, they've already given us that information. They're telling us that it's filled at a constant rate of 15 litres every minute. So we can come to dv by dt in a minute. First we need to differentiate this. So dv by dt, what will this be? Well, if I differentiate this, that's going to be pi over 3.6 squared, like usual, on the outside here. This is going to be times by e to the 2h now, so e to the 2h. This will be 5.2 e to the h, nothing will change with that. Like so. And then finally, we're just going to get plus 6.76 here. Okay. So now we've got dv by dt. I just need to take the reciprocal of this, but we know h is 0.2 meters. So when h is 0.2, okay. So I'm gonna have to plug that into my h now here in this dv by dt. So if you plug that in, what you'll get is that dv by dt is equal to 3.539 and so on. So what we need is 1 over this. So therefore, dt. Sorry, this isn't dv by dt. This should actually be dh by dv, or dv by dh. I'm half asleep. dv by dh, dv by dh. So we want now dh over dv. Okay, I'm making a lot of mistakes today, so I do apologise. dh over dv. So this will be 1 over 3.539. Okay, so we've got dh by dv now, so we can use that in the chain rule here. Now we just need dv by dt, so this is going to be equal. That's going to be equal now to 1 over 3.539 times by. So it's being filled at a rate of 15 litres every minute, and that's every minute. We want the answer in terms of an hour, centimetres per hour. So it's going to be, now remember, it's in litres. We don't want this in litres, we want it. So we're going to have to divide here. It's going to be 0.015. Okay, 0.015 times by. Now that's per minute, so we need it by hour. So we're going to have to times it by 60 to give us 1 hour. Okay. Now if you put this in on your calculator, what you'll get is you'll get 0.254. But remember here now, my rate isn't 0.254 because when we plugged our h in, it was in terms of meters. The answer is in centimeters. So where we plugged in a h here, we did this twice. So we're going to have to times this by 100. Times that by 100. So doing that, we're going to get 25.4 centimeters per hour. And there we have it. So that's question 8, fully complete for the full paper. If you're new around here, be sure to subscribe. I'm going for all the new further maths exam papers.